Hello again, welcome back. Let's consider another aspect of atomic stability, another way in which atoms can gain stability. Let's continue our discussion of chemical bonding, and this time we're going to be looking at covalent bonds. In covalent bonding, we're going to be doing something quite a bit different than what we did in ionic bonding. In covalent bonding, we're going to have atoms sharing pairs of electrons. Now remember, the reason they're doing this is the same reason that they gained or lost electrons when we talked about ionization before. They're trying to become more stable. Now, whenever you see a drawing of a molecule, and we're going to see lots of pictures of organic molecules in your textbook, you'll see that these covalent bonds are drawn as a solid line. We're going to be working with covalently bonded molecules mostly this semester. That'll be the key discussion that we're going to have in terms of our next chapter. Is going to be a wide variety of covalently bonded molecules. Now, remember that each one of those lines, when I have a covalent bond represented as a line, each time that represents one pair of shared electrons. So, we might see something like two hydrogen atoms drawn with a line between them, and that would suggest that these two hydrogens are sharing one pair of electrons. Also, in something like carbon dioxide, carbon and two oxygens, notice that there's a line between the oxygen and the carbon, and that means that carbon is sharing two electrons with each of those oxygen atoms. Remember, they're doing this to attain stability. In a little while, I'm going to actually draw you some pictures of some of these electrons being shared so we can get a better idea of what is meant by them being shared between two atoms. Now, one of the ways you're going to see these molecules that are held together by covalent bonds represented is by what's called a molecular formula. That's sort of a chemical shorthand. It's just a way to try to relate the composition of a molecule in terms of the number of atoms that are present. So, for example, those two hydrogen atoms that we talked about in the previous illustration would be written as H with a subscript 2, meaning two hydrogen atoms attached to each other. It doesn't necessarily give us detailed information about where these bonds are or how they're arranged, especially when we look at larger molecules or some of these other examples like H2O. Well, that's two hydrogens and one oxygen, a fairly simple molecule. But then we have something like C6H12O6. This would be, something like glucose, a carbohydrate, a simple sugar. And you can see that I know that this structure has 6 carbons in it, but I really don't have any sense for, how are they attached to the hydrogens and how are the oxygens attached to the carbons, and in other words, what are the bonding relationships? So a molecular formula gives you one type of information, and that's going to be different than the kind of information we got from a structural formula. Structural formulas show you the bonding relationships between atoms. They show you where the pairs of electrons are being shared. Molecular formulas are a shorthand way of showing you the composition of a molecule, how many of each kind of atom is present. And notice that in each case, the number of a particular atom is shown by this subscript. So in carbon dioxide, CO2, that means that we have one carbon and two oxygens. Nice way to simplify the description of one of these molecules, especially if it's a very large molecule, but not a lot of detail is involved in this type of representation. Let's take a look at this table, and what you can see is different ways in which we could represent the sharing of paired electrons that make up covalently bonded molecules. First of all, in the first column, you can see that we have some molecular formulas. That's what we just spoke about, just describing the number of atoms that are present. On the right-hand side of the illustration, we have those lines representing the covalent bonds that are associated with the pairs of shared electrons. And in the middle is an electron configuration, and this is the type of representation that you least commonly see, but it's a good thing to look at because it will give you a sense for what's actually happening. For example, take a look at the H2, the hydrogen gas molecule at the top. You can see that each of those hydrogens is contributing, think of it that way, their electron to the shared pair. And if we considered what's going on from this hydrogen's perspective, If it looks out, so to speak, to its first valence shell, it's going to see 2 electrons present in that first valence shell. It feels stable. Its partner also feels as if it has 2 electrons in its first valence shell, and that means that both of these atoms feel stable, feel as if they have a filled electron shell. Now notice on the right-hand column that there's also a representation of a double covalent bond. Remember, each line represents 1 pair of shared electrons, so if I have 2 atoms with a double covalent bond, that would mean they're sharing 4 electrons, 2 pairs. Notice the electron configuration illustration showing that those 2 oxygen atoms are indeed sharing 2 pairs of electrons. Again, their goal is to gain that sense of stability. So you're going to see all 3 kinds of representations in your book, but we're going to see primarily those that are molecular formulas and also representations that are structural formulas. So now let's consider how these electrons might be shared. One of the things we're going to see is that we're actually going to have 2 classifications for covalent bonds, and they're going to be based upon how the 2 atoms involved are sharing their electrons. Not every atom on the periodic table has the same pull on its electrons. Some atomic nuclei pull more strongly on the electrons moving in their electron cloud than others do. That quality, that tendency for how much an atom pulls on its electrons is called the atom's electronegativity. Now, that's a very large word, and it's not something that we're going to worry about determining the electronegativities of atoms, but of the atoms that we are going to deal with, I want you to know that we're going to deal with 2, what I like to call electron hogs. Oxygen and nitrogen have the 2 highest electronegativities of the atoms that we're going to deal with on a regular basis. Remember, the atoms that I said we were going to talk about most are that big 6. CHNOPS, right? And of those big 6, oxygen and nitrogen are definitely the ones that have the highest electronegativity. Now that's going to create some interesting situations when oxygen or nitrogen share electrons with other members of the big 6, carbon, hydrogen, phosphorus, sulfur. We're going to see some interesting relationships in terms of how they share those electrons. So, what we're going to look for is how electrons are being shared, and then how that affects the type of covalent bond that we possess. If you have 2 atoms that have the same or very similar electronegativities, in other words, if they have the same amount of pull on electrons, then what's going to happen is they're going to share their electrons equally. Realize what I'm saying. If I have 2 hydrogens sharing electrons, like in H2, well, they both are the same atom, so they're going to allow those electrons to spend an equal amount of time with each hydrogen atom. If I have 2 oxygens sharing a pair of electrons, also, those electrons are going to be shared more or less equally. And, for the most part, if I have any sharing that goes on between carbon or hydrogen or phosphorus or sulfur, those 4 members of the big 6, we would expect them to more or less share a pair of electrons equally. It's only when we have oxygen with one of those 4, or nitrogen with one of those 4, that we begin to see this unequal sharing of electrons. We're going to see the oxygen or the nitrogen hogging those electrons. So what I'd like to do is I'd like to take a moment to actually draw you an illustration to show you what this equal and unequal sharing of electrons might be thought of, or a way for you to visualize it. Let's take a look at an illustration. If I have something like 2 hydrogens sharing a pair of electrons, remember there's 2 electrons here represented by that single covalent bond. If I was going to try to represent the path those 2 electrons take, I might do it in this form. And what I'm trying to imply is that those electrons are spending an equal amount of time with one atom as they do with another atom. They're being shared equally. But now what happens if I have something like hydrogen sharing a pair of electrons with an electron hog like oxygen. Oxygen has a much greater electronegativity than the hydrogen, and as a result, these electrons are going to be shared unequally. Look what that's going to do. Think of it as the electrons spending some time here and some time there, but if I was going to try to draw a representation of this, I might do this. Now I know that this is not an accurate representation of what actually occurs, but I just wanted to give you a sense for you to think about what's happening in this unequal sharing. You can see what I'm trying to represent. That pair of electrons are spending more of their time here and less of their time over here. The result is that this end of this covalent bond is going to have a slight negative charge. And that means that this end of that covalently bound pair of atoms is going to have a slightly positive charge. Anytime I have any kind of structure that has different ends, and clearly here we have different ends in terms of the charges that are present, we call that structure, we say it has the quality of polarity. So that means that we would refer to this covalent bond as a polar covalent bond, and we'd refer to this covalent bond as a nonpolar. All right, so again, this is a crude representation, just trying to get across the idea of what's meant by equal versus unequal sharing. All right, so let's consider what that's going to do for us as we look at molecules that we see in the textbook or pictures of molecules that we start to work with as we get into other chapters. What I want you to do is you want to think of oxygen and nitrogen as being like flags. Anytime you see oxygen or nitrogen sharing electrons with other members of the big six, you immediately want to think to yourself, boy, I bet you that's going to be a polar covalent bond. That also means that that part of the molecule is going to be considered a polar portion of that molecule. What this also means is that we're going to expect that part of the molecule to have some charges on it. Now, water is a wonderful example of a polar molecule, and there are a number of videos that deal with the properties of water and this polar nature of water, and you're going to want to make sure you take a look at that as a good example of a molecule that's being held together by polar covalent bonds. Now, what this means is that oxygen and nitrogen, these electron hogs, are going to be our flags for us to expect or anticipate a portion of the molecule or a molecule itself having polar covalent bonds, being polar, and therefore having charges. Now, think for a moment what it means if we have electrons, however, being shared by two of these electron hogs. If I have oxygen and nitrogen sharing a pair of electrons, since they both have very high electronegativities, that bond would actually be nonpolar. So notice, oxygen with oxygen, oxygen with nitrogen, nitrogen with nitrogen, those are all examples of nonpolar covalent bonds. It's when I have oxygen with carbon, or nitrogen with hydrogen, or oxygen with sulfur. Those are the places that I expect to find those polar covalent bonds. Please use this as a rule of thumb to help you make determinations about whether molecules are or are not polar, whether they do or do not have charges. For example, if I have carbon and hydrogen sharing electrons with each other, those are two non-electron hogs. I'd expect them to have a non-polar covalent bond. No charges present. This will become an important idea when we begin to talk about organic chemistry and the properties of the different kinds of organic molecules. All right, so let's go back and consider what we've looked at this time. Once again, we started off with the basic idea that atoms want to attain stability, and one way to do that was to share electrons. Why do I share my electrons? To try to get a filled valence shell. In doing so, as I share electrons with other atoms, I'm going to be forming covalent bonds. Now, covalent bonds can either be the result of an equal sharing of electrons, and therefore they would be a non-polar covalent bond, or that covalent bond could be the result of an unequal sharing of electrons. Remember, that's where our electron hogs come in, oxygen and nitrogen, and then we would expect to find a polar covalent bond. Now we're going to continue this idea of talking about charge and polarity in a number of other videos, and I look forward to talking to you next time about some of these interesting properties.